Okay, thank you for sticking out to the last talk of this session. So this is a joint work with Brian Swingle, who is from University of Maryland, and also part of this work was done while I was also at IBM. So lately, I've been thinking about what the field is going to look like from like a couple of years from now, and it's mostly because there's a lot of public interest in quantum computation. So if you look up news articles from Google, it's not too difficult to find news articles about quantum computing. And I found it amusing that from last year, from 3 different companies, everybody was saying that from 5 years from now, something interesting is going to happen. So this suggests that, well, you might have a differing opinion or the same opinion, but at the very least, this seems to suggest that there's a public expectation that something dramatic might happen over the next few years. So I begin wondering, so like 5 years from now, how would the field look like? Would it still be like booming and like with the increasing number of submissions to QIP, or will it be like in the winter where the things are a bit declining? I'm to be clear, I am very optimistic about the future of the quantum computing, but because there is so much hype nowadays, it's sort of hard to ignore about these possibilities. Whatever the case might be, right now, I think everybody would agree that there is a big gap between the dream and the reality. What would you like to do is to solve important industrial problems that cannot be solved with the existing computer, with the quantum computer. But the reality is that the quantum computers that we have right now are far too small and noisy, so we can't quite achieve that. And the biggest problem is, of course, the noise. So like I actually dig down the literature to see like why the classical computers are so has such a low noise rate. Apparently, like at some point in history, already in the 90s, like the primary source of errors was the cosmic rays that were hitting a particular component of your integrated circuit, which is why apparently already in the 90s, the error rate was in the order of like 1/10⁵. It's such a small number, we don't really need to care about it. But for quantum computers, like right now, even with the best technology, the best error rate for the 2-qubit gates is around the order of like 1/10⁵. And this is kind of a problem because let's say you have a quantum circuit, and let's say you want to apply a set of unitary gates, and then you want to read out an output. Right, so here's your output bit. And if there's a constant noise rate, what's going to happen is that there are these spots in which the errors could have occurred. So the larger the circuit size becomes, there are more spots in the circuit that which can be potentially vulnerable to noise. And in principle, in the worst case, a single error can flip the output of your answer, in which case the answer that you get may not be so reliable. So the bottom line is, the deeper the circuit is, there are more error locations, and this is a problem. So there's this like a dilemma when you think about this problem. So like because you want to have a quantum speedup, the natural thing to do is to increase the quantum circuit size. But if you increase the circuit size, then eventually you realize that too much noise will accumulate. So if you decrease the circuit size, you're back to square one. And this is kind of a vicious cycle. And one of our motivation was to find a special instance in which this cycle can be avoided. So if I were to show like one slide, it will be this slide. So what we will show is that there's a class of quantum circuits that we call as noise-resilient quantum circuits, which has this somewhat counterintuitive property that even if you increase the circuit size and even if you don't do error correction, there's a sense in which that the noise does not accumulate too much. Of course, you should be very skeptical about such claim because, like, let's say if your error rate is like 50%, clearly that's not going to do anything useful. So there's some subtlety in this argument. So what do we really mean? So roughly speaking, you should view a noise-resilient circuit as a circuit whose output distribution restricted to local observables gives you a relatively reliable result. So let's say without loss of generality, you consider a k-local operator O. Okay, and you want to evaluate its expectation value over some state generated by some quantum circuit. And you want to compare its expectation value when the error is exactly 0 and when the error is epsilon. And here, error, I mean really error in every sense of the word, like measurement error, preparation error, and gate error. And what I want is that for these local expectation values, where k is order 1, the deviation is like order epsilon, as opposed to order epsilon times like n to the some power, where n is the total number of qubits. And what's non-trivial is that there are noise-resilient quantum circuits that are not short depths. So I'm going to get into details of like how you construct such circuits. But for now, let me take a brief moment to talk about like what we're going to do with these things. So our basic proposal is to contract tensor networks on a noisy quantum computer using noise-resilient quantum circuits. So whenever you have a proposal to use a quantum computer, there are these like typical questions that you have to ask. Why is this task classically hard, and why is this useful, right? But in this talk, because I care about noise, I want to ask this extra question, namely, what is the mechanism behind this noise resilience? So these are the three main things that I would like to deliver in this talk. Here's a super short version. Hardness-wise, there's a sense in which these circuits are hard to simulate classically. We were kind of unsure about this, but one of the referees actually pointed out a reference which turned out to be somewhat relevant. Thank you. And and the circuit, there's a sense in which it does something practical. So namely, these circuits can speed up the tensor network calculations for strongly interacting quantum many-body systems, which appears to be hard classically. And the main mechanism behind noise resilience is the stability of hidden dissipative dynamics, and I will get into the details about this towards the very end. Again, I just want to reiterate the formal definition. Roughly speaking, noise-resilient circuits are something which are robust, which gives you robust answers for local expectation values. But it may give you like completely wrong answers, like if you consider an order parameter that is, let's say, for like observables where k is like, let's say, order log n or order n. So for those observables, I can't say anything. Because of the interest of time, I can't go into all the details of the particular circuits, but I can give you some like pictures on how they look like. So the first instance is, you can think of it as like a 2D version of a finitely correlated states. If you don't know what that is, you can think of it as like a special subclass of PEPs, or like 2D version of the subclass of the matrix product states. And the way you basically make these states is that you prepare a product state, and you have these like ancillary system, which is like a one-dimensional ancillary system, and it travels along the x-axis, interact with individual rows, and move on to the next axis. There's a second instance, which Brian and myself call as a DMERA. We named it as DMERA because it sort of sounded cool. And it's basically more or less a variant of MERA, which was proposed by Vidal. Also, there was a related work by Evenbly and White. And the circuit looks like this. The time goes from top to the bottom. So what you do with these things is that basically you apply this circuit on your quantum computer, and so that's the input, and down here you have output. Again, like here, I guess this is technically speaking not a circuit, but you run the circuit, and then you measure any local observable that you want. Something that is like located here, or let's say here, okay? And these local observables can be anything that you want. It can be like energy or magnetization or like other order parameters that you might be interested in. And I should mention that this is a side comment, but tensor networks can actually, people use tensor networks because they have good reasons. It's because you can accurately approximate ground states of many physical systems with a moderate number of parameters. And this comes from a lot of like numerical studies, and also some theoretical work on the approximation guarantee. So without the, so if you couldn't actually approximate the ground state reliably with these methods, like this wouldn't have made any sense. But because they can actually approximate these things very well, it actually makes a lot of sense to use these as an ansatz to approximate ground states of interest. Okay, I'd like to talk about the hardness very briefly. Apparently, contracting a tensor network up to an additive approximation is PQP complete, which is what we intend to do. And this was pointed out to us by referee 2. But having said that, this paper, the class of tensor networks that we consider in our paper is way more restrictive than what was considered in this paper. But one of our proposals, in the worst case, takes exponential time in the classical computer to simulate. So we expect there might be some subtleties, but we expect there to be not. I don't think there will be like a naive classical algorithm that can carry out what we are going to propose. And you might ask whether this method has any practical usage. And whenever people ask me this question, I like to put myself in the shoes of like material scientists. I'm not a material scientist, but basically my understanding is this. So if you're someone who's trying to make a new material, one way in which you can speed up your like material discovery process is to predict the material as opposed to just going to the lab and try everything that you can. And one way to do this is that you have a class of materials that you have in your mind, and then you come up with a model that you think describes the material relatively well, and then you plug in this model into your computer, classical computer or quantum computer, and then you extract the material properties. And the thing is, many of the material properties, like the energy or the conductivity, can be often computed from correlation functions, which can be supported on like order 1 number of sites. And at the end of the day, the purpose of these like quantum simulation types of application is to save either time or money to searching new material. And it's important to realize that at the end of the day, the answer that you want it does not have to scale with the precision of the answer that you want does not have to scale with like 1 over poly n. At the end of the this is what my condensed matter physics friend told me once. You can read it, but just to reiterate. They say like unlike high energy physics where they make a big deal out of like doing like complicated like Feynman diagram calculations, condensed matter people like don't care about that too much because all you care about is like it's about the qualitative properties of the material, whether it is insulating or not, and what's the magnetic susceptibility, things like that. And these properties can be often inferred from some order parameter, which can be estimated from simple correlation functions, for which the noise-resilient quantum circuits give you a reliable answer. Okay, so like the kind of things that you can study are probably something like this. So you can calculate things like energy per unit volume, which gives you Young's modulus, and magnetization or heat or electrical conductivity. So in case you're not familiar with this business, the way it works for computational methods is that you have a challenging lattice model, and what you do is that you have a bunch of methods. So all these complicated acronyms, these represent different computational methods. And here on the y-axis, you have an energy that is normalized by the total number of sites. So it's an energy per site. And as you can see, like different methods are competing to each other. And this particular thing, like energy per site, is a kind of thing that the noise-resilient circuits will be able to produce in a robust fashion. Okay, so enough of the background. So I want to go into the main meat of the talk, which is that why are these local expectation values stable to the noise? What is the main mechanism? And to do that, I'd like to begin by identifying the main challenge. So the point is, if you only consider shallow quantum circuits, the outcome that you get will be noise resilient trivially. But the thing is, there are quantum many-body systems for which shallow quantum circuits do not give you a very good approximation. This fact was pointed out by Bravi Hastings versus Rada in 2006, and also by Jens Eisert and Tobias Osborne. Basically, the point is that if you have a topologically ordered system, and then at least one of the ground states must have a lower bound of the complexity to prepare the ground state. So if you restrict your class of ansatz to shallow quantum circuits, you inevitably miss out on these particular states. And that's not good because you are biasing your simulation into a particular direction. So one may expect, because of these examples, that the circuits that prepare, let's say, topologically ordered states would be susceptible to noise, because naively, the number of gates to prepare this state would scale like a super linearly with the number of sites. And this will naively give you some error bound that scales like epsilon times n to the c, where c is not 0. But what we can claim is that actually there's a better error bound. Which is an error bound for not the global state, but error bound for correlation functions, which scales like order epsilon. So here, A is assumed to be like an order 1 size subsystem. So for predicting the material properties, up to let's say, a precision epsilon, it would suffice to have a quantum computer with noise rate of order epsilon, as long as you are only caring about the class of states which can be well approximated by tensor networks. So the way you derive the naive error bound is not too difficult. So if, let's say, you have a quantum circuit like this, and let's say you want to measure a local observer that is down here, what you do is that you basically count the total number of gates that can potentially influence this site. So in our circuit, it'll be that set will be the set of like red boxes basically. So like if you have a generic quantum many-body system partitioned into like B and A, where size of A is like order 1, the way you bound these things is that you bound this should be the diamond norm distance. So G is a noiseless gate and Gn is like a noisy gate. And you assume that their difference in the diamond norm is like order epsilon. And then you just use a bunch of triangle inequality to bound the difference between the global state, the noiseless global state and the noisy global state. And then you just use the monotonicity of the trace distance under like quantum channel. And you get this somewhat lousy bound. So clearly this naive error bound is not going to work. So you have to do something smarter. So how do you do that? So our approach was to basically look for ways in which this could possibly happen. Okay. And fortunately, we didn't have to look that hard because we were aware of a very nice result, which was presented at QIP roughly like 4 or 5 years ago. And this result is the stability of local expectation values to perturbations in rapidly mixing quantum-tate dissipative systems. It's quite a mouthful, but I'll explain what that is. I believe many of these people are maybe in the audience, so you might want to like probe them if you have more technical questions. But I'll get back to that later. And there's a second fact, which is that in these tensor networks that I described, often the expectation values of any local observables turns out to be exactly equal to the expectation values of local observables undergoing some dissipative dynamics. And this is like an extremely well-known result. Like this was known from this like finitely correlated papers from the 1992, and also in the Mera case, this was pointed out by Evenbly and Vidal in 2007. It's almost a trivial fact. But like if you join these two facts together, you get something non-trivial, which is that in tensor networks, there's this hidden dissipative dynamics, which goes on for a long time. So the total number of time steps in this dissipative dynamics scales with the depths of the circuit. And the problem was that the depths of the circuit in general would scale at least, it will not be a constant in general. And what saves us from getting a lousy error bound is this stability result by Lucia et al. So what they showed was basically the following. So if a dissipative dynamics mixes local observables fast, then the dynamics is stable to perturbation. So here, I gave a sort of like a cartoon version of their actual statement. So you can think of M as a local observable, which is supported on a subsystem of size order 1. And L is a Lindbladian that generates some dissipative dynamics. The important thing to remember here is that L is a sum of local Lindbladians. So the norm of L is unbounded. And L prime is a perturbation of L, wherein each of these local terms are perturbed by order epsilon amount. So what's interesting about the result is that if you if you try to bound the difference between L and L prime, because this is a sum of local Lindbladians, each of which have like order epsilon diamond norm strengths, the total norm of L minus L prime can be actually unbounded. And the main point of this theorem is that despite this unboundedness, you can still show that these two things are close to each other, like only up to like order epsilon. So the proof is actually pretty straightforward. Like once you define what it means for local observables to mix fast, and it follows from a telescopic decomposition. If you know it, you know immediately how this thing goes. If you don't, you can ask me later. And in our case, because we have this tensor network, which can be viewed as a, from the perspective of local expectation values, can be viewed as a sequence of dissipative maps. Instead of this like continuous time thing, we have to derive an analogous version of discrete time dissipative evolution, which can be straightforwardly dealt with. So let me give you an example. So this is what we call as a deep Mera. Well, it's actually a Mera, but as I said, deep Mera sounds cooler. And so here are the parameters. So you have a one-dimensional system consisting of L sites, and the total depth of circuit is actually, this should be like 2 log L actually. The point is it's like order log L, so it scales with the system size. So let's say you want to compute the expectation value of this local observable that is located down here. So these red boxes are a set of gates that can potentially influence O, whereas the blue boxes have absolutely no influence on O. And you can see very easily, at least for the blue boxes down here, Well, these are just unitary gates which have like absolutely zero influence on this O. So if you write down the expression for this local expectation value, what you can immediately realize is that this is exactly equal to an expectation value of another observable, as let's say phi of O, with respect to another state, psi of n minus 1. And psi of n and psi of n minus 1 are related by like a finite depth quantum circuit, and O and phi of O are related by some quantum channel. So phi here is some linear map that maps operators to operators, and it has some nice properties that we can make use of. So you can sort of see the similar structure. So like, for instance, there are these like 5 boxes that are grouped together, and there are these like 5 boxes grouped together, another 5 boxes, and the pattern repeats. So you can just repeat this idea many times. So this expression turns out to be exactly equal to, let's say, applying phi twice to O, and then evaluating the expectation value with respect to this like a smaller wave function, which in turn is equal to that, and etc. Okay. So it turns out that by construction, this map phi is a unitole quantum channel. And in the previous slides, I told you that there is this nice result by Lucia et al., which showed that if you have a rapidly mixing dissipative dynamics, you get some stability. It turns out that phi is like rapidly mixing, quote unquote, under a physical condition. So I will tell you what this physical condition is. I'm not going to sweep this under the rug, so don't worry. But what I do want to emphasize here is that if you don't use this fact, the naive error bound will give you like order n epsilon error bound. But by using the stability of the dissipative dynamics, you can get a better error bound, which scales like order epsilon. Let me make some technical comments. So this bound, this basically follows from the telescopic decomposition plus the rapid mixing assumption. Again, if you're curious, you can ask me later. And the proof only states the infinite time limit, but the finite time case works out roughly similarly. The only subtlety that you should be worried about is that in the infinite time case, like it doesn't really matter like what your initial state is, but when you take the finite time case, the initial states must be close to each other in a certain sense. So the care must be taken for the preparation and the measurement errors, which we deal with. And as I said, the generalization to the discrete time evolution is pretty straightforward. I have a physics comment. Namely, you should ask this question, does this rapid mixing condition hold? Like, when does it actually hold? So it turns out that we have like 2 differing answers to these like 2 different proposals. In the first proposal, which was done by myself, we have this 2D tensor network, which I showed you before. And we can sort of check this on a case-by-case basis, but so far we have only verified for a torico. But having said that, we have a general theorem under which, if it is satisfied, guarantees to stability. And my guess is that there is a wider class of systems for which the stability bound holds. For DMERA, we actually have we can say something more generally. And this is because the mixing condition fails if there are observables whose correlation decays slower than the power law. So like, let's say like 1 over like a log of the distance, or like a actual long-range correlation in the Ising model. So the bottom line is, if you have a model, and if you have like a lattice model, and if you believe that the correlation will decay like a power law or like a slower than that, then the DMERA would be a good approximation, which means that you can expect the noise resilience to come into play. The important part is like the speed up and the error. So basically what we're doing is just running a quantum circuit on a quantum computer. So it's not too surprising that at least in the absence of error, that it will be difficult to simulate this classically. So if you just plug in the numbers, so just to set you the parameters, n here is okay, this, maybe it was like affected by this area, but this is the number of qubits, and chi is the number of variational parameters per site. So remember, this is a variational approach. So the larger number of like variational parameters you have, better approximation you get. But the hope is that with a moderate number of chi, you can get a still very good approximation. And d is the number of spatial dimensions. And as you can see, as I said, it's not too surprising to see a speed up of some sort when it comes down to contracting the tensor network. And assuming that this value of chi is moderate, the error turns out to be like order epsilon tilde chi cube, where epsilon tilde hides the polylogarithmic factor in 1 over epsilon. And in the second case, we have like order epsilon times chi to the plus 1. The key takeaways is that, first of all, that there are large depth quantum circuits that actually don't produce jump, unlike what you might naively expect. And the key mechanism behind this is the stability of the rapidly mixing quantum systems. And, well, okay, so I believe they are scientifically useful. So I'm kind of agnostic about like whether the tensor networks will be like will play like an extremely important role in the long run. But like bottom line is they have showed a lot of promise. And if you believe that tensor networks are scientifically useful tools, then I believe our results suggest that with the quantum computer you can do something even more. So here are some open problems. First of all, as I said, for our 2D tensor network model, we couldn't show that the stability result holds for like extremely wide class of models that we wanted to hold. So it'll be nice to have a more general sufficient conditions for the rapid mixing condition in these like tensor network methods. And there is a logical possibility that for these algorithms, maybe the noise resilience will help you in coming with a better classical algorithm. In that case, the correct route would be to like use these like better classical algorithms to boost the existing tensor network calculations. Either way, it'll be an improvement. And there's this like gory details on like how many qubits and how low of an error rate would we need to actually declare a conclusive advantage over the classical computers. This needs some work. Lastly, when I gave this talk in different places, I was always asked this question, like, can you use this idea to like do something more like practical, like industrially, like appealing? And okay, so honestly, I don't have an answer, but I do want to mention that if you look at the history from like 40 years ago, there was this thing called density functional theory, which was not used as like any industrial purpose at all. But now, like, it's pretty much the modern workhorse of like academic or industrial material search, and I don't see why this wouldn't follow the same history. So my answer to this question is that probably in the future you can expect this to be useful at some point. Okay, with that, I would like to end with a somewhat provocative slide. Thank you.
Thank you for the talk. Okay, we have time for questions.
Sometimes when people ask me what quantum computers are going to be good for, I jokingly say, well, they're going to help us build better quantum computers in the future. Mm-hmm. And we know, for example, from the work of Yao Yanqi and others, that you can actually express quantum circuits as tensor network contractions.
That's right.
Could that be a target here of nearer-term quantum computers, helping us understand and study approximately, since you have approximate tensor network contraction, quantum circuits on larger quantum computers?
That could work out. So like this Arad and Landau paper actually gives a prescription to like contract the tensor network on a quantum computer, like even when it's not obviously a quantum circuit. But I haven't looked into details on how all of this will carry through. But this doesn't seem implausible.
Okay, thanks.
Hi, just trying to understand your motivation a little bit more. As motivation, you said, you need high-depth quantum circuits to understand topological order or critical states, right? But for those systems, you can't really use local correlations to identify topological order, for instance.
Right.
So it doesn't seem to be applicable in those cases, right?
That's right. So I was worried about this, but then I looked at the history of like how people like study like topological order, and like nowadays like people have good numerics to see these non-local features, but like for a very long time until like 2010, before there was this paper by Steve White and David Hughes and sorry, there's another person, but. Before that happened, what everyone did was that, oh, we look at this order parameter and we see nothing, and that's the evidence of topological order. compared to like, let's say, seeing a magnetization. So the point that I'm trying to make here is that even though topological order systems will not like, you won't be able to probe these non-local features, you can still tell that this is not a like locally ordered system. So, and that is still some non-trivial information. Okay, so like between the two, you can distinguish. I mean, so there's some sort of art here, right? I mean, of course, if you measure an order parameter and if you see nothing, that does not necessarily mean that it's a topological order. But you can go through a number of tests to see to check your hypothesis, and this is what people had been doing until 2010.
I still think it would be hard to do with local order parameters, but okay. Yeah.
We have another question here.
Thanks, Isaac. That was awesome. So there was, I guess I don't quite understand how necessary the tensor networks are. So you were using this rapid mixin theorem that basically just said as long as you have some like Markovian evolution and it's rapid mixing,
Yes, yeah.
then you have this resilience gate noise.
That's
So then
right.
you went on to show that if you have these tensor networks, then you satisfy the conditions of the rapid mixing. But say if I just had some random system, is there any reason why if I was just working with qubits and I knew for some reason that I had a Liouvillean that had as a fixed point, say, the ground state of some Hamiltonian, like a quantum chemistry Hamiltonian,
Yeah.
fingers crossed,
So
and was rapid mixing,
Yeah.
then it would work, no?
this is a very good question. So, but the answer is kind of going in a different direction. So the point is, so what you would like to do is something like this. So I can write down a Hamiltonian, and I want to find its like a finite temperature Gibbs state or its ground state by some rapidly mixing operation. But the problem is, unless this Hamiltonian consists of sum of local terms that commute with each other, this like Davies generator that whose fixed point is this e to the minus bh state, it does not consist of local terms. So, and this is kind of a big open problem in this like Davies generator business. So, like, and indeed, like when the Hamiltonian is sum of local commuting terms, there are these prescriptions like Brandao-Castellano prescription where you can use. And indeed, like that I think will be a better approach. But for like general Hamiltonians, that approach will not work, as far as I can see.
Thanks.
All right. Let's thank Isaac and all the speakers of this session.